Good morning, North America, and good evening to the rest of the world. This is Swami from APA Engineering, welcoming you, each one of you, for this webinar that is going to be presented by our subject matter expert, Dr. Aucejo, fondly known as Vicente to us. So I thank each and every one of you again for joining this electromagnetic simulation webinar that has been jointly done by APA Engineering and NDLEC. And I've been honored as well to give introduction about our company APA Engineering in short, and as well as to introduce our expert Dr. Aucejo and his credentials. So APA Engineering, as you can see in the screen, we are a 20 plus years of old company having 350 plus employees and 350 plus clients. So you can see that each employee has one client to make the figures look easy for you. And we are very proud to say that we are ISO 9001 quality certified, as well as ISO 27001 data security certified company. And very recently and very proudly as well to let you know, we are a TISAX certified company, which is a mandatory certification to work with top OEMs because that has been only then we can work with the top OEM companies and do services to them. Talking about APA Engineering, we have 4 different service lines, especially engineering, that's where we present at now, and sourcing and compliance and IT are the other 3 divisions along with engineering, where we have a presence all over the world. To name our the headquarters, it's in Chennai, southern part of India, and you can see on the left hand side of the screen our office with all our colleagues standing there and giving a smiling pose. And to give a small intro about our clients, you can see in the next slide. There you can see ABB, Toyota Basuku, Vogue Warner, Nival, and especially when I talked about TISAX certification, we got it to work with the company BMW. I'm sure that will ring a bell because, as I told, they have the topmost data security system to be in place to work with them, and we are proud to say that we have been awarded with the certification of TISAX. And to talk about the expert today who's going to present the webinar, Dr. Aucejo. He is an electrical and electronics engineer from 1997 and have 20 plus years of experience, and also very proud to announce he is a PhD holder from electrical engineering from the University of Paul Verlaine in Metz, Spain. So I hand over to Vicente to move ahead with this presentation today and not to hold anything more. It's all yours, Vicente.
Thank you very much, Swami, for your introduction. Thanks also to all attendees for joining this webinar about designing and simulating an electrical motor for e-mobility. And let me show you the agenda for this webinar. First, we will have a brief introduction. Then we will review some main components in an electric vehicle. We will introduce the different electromagnetic structures for e-mobility, and later we will carry out a practical example designing a permanent magnet synchronous motor for an electrical vehicle. So to start, we should point that the energy developed by a vehicle is used in overcoming the inertia and acquiring kinetic energy, acquiring potential energy, and overcoming the drag torque, that is both aerodynamic and rolling friction torques. Electric motors have the ability to work either as a motor or as a generator, and using batteries, the energy produced can be stored. It is estimated that in a Euro cycle, 60% of the energy consumed is used to overcome the inertia and this is recoverable energy. In urban circuit, the average speed of travel is less than half on the road, then the energy lost in friction is very low. Besides, the efficiency of an electric motor is higher than an internal combustion engine motor. So we can conclude that with e-mobility, it is estimated that consumption in urban circuits could be less than a half on that on the road. The goal of this webinar is to show you the essential of electrical vehicles motoring, but also to show you how to simulation can help you, not only to design electric motor for e-mobility, but also to take into account aspects that in the past were roughly estimated, like lightweighting, structural analysis, noise and vibrations, drive and control, thermal analysis, and performance analysis. Thanks to the simulation using Altair software, Porsche published that simulation helped them to take more informed and earlier design decisions, better performing motors, and accelerated time to market. The main components in an electric powertrain are the storage elements like the batteries and supercapacitors, the inverters to supply the electric motor and charge the batteries, of course, the electric motor, which is the main topic of this webinar, and finally, the microprocessor, which manages the whole system. Electric motors have a rotating part named rotor and fixed part named stator. Typically, the rotor is inside and the stator is in the outside of the motor. To get the movement of the rotor, the motor needs to produce a torque by means of two magnetic fields, one in the rotor and the second one in the stator. And the only two magnetic field sources that we know are electric currents and permanent magnets. In an electric motor, we can find four circuits: electric circuits, which are mainly the coils, and they are made of copper. Magnetic circuit, which are made of iron sheets, dielectric circuit, which is made of insulators, and the cooling circuit to remove the heat from the motor. Several electromagnetic structures can be used for e-mobility, and we will have a look into them. We can find the induction motors. We can find also permanent magnet synchronous motors, switch reluctance motors, brassless DC motors, and axial flux motors. We will start with induction motor. They date from the end of the 19th century, and they are the most widespread in industry due to their robustness, low cost, and low maintenance. Induction motors powered by electronic converters are replacing DC motors in drives where variable speed is needed, like e-mobility applications. There are two types of synchronous machines: wound rotors and squirrel cage rotors. In the picture, we can see this kind of rotor. Instead of windings in the rotor, we can see the rotor has rotor bars, and they are sorted with the two end rings at each side of the rotor. The working principle of this motor is that we get a magnetic field from a three-phase current, and the winding made of coils shifted 120 degrees. Each phase creates a pulsating magnetic field that the sum of the three phases is a rotating magnetic field in the area. Then an electromotive force is induced in the rotor conductors which are shorted, and current flowing on those conductors generate a second rotating field in the area. Interaction between the two magnetic fields generates an electromagnetic torque which makes rotor rotate. Rotor turns at lower mechanical speed than the stator magnetic field. That is why those motors are also known as asynchronous motors. The difference between the two speeds is known as slip, and usually it is between 2 and 6% of the synchronous speed. The second electromagnetic structure are permanent magnet synchronous motors. The origin of this machine is the synchronous machine, replacing the rotor winding supplied with DC current by permanent magnets. We get the permanent magnet synchronous motors. This machine has been typically used in electric energy generation. The characteristic of this machine is very appreciated because frequency depends on the rotation speed, and this quantity it is very easy to control. There are two types of synchronous machines: salient poles machines and cylindrical rotor. Nowadays, the use of the motor is increasing because this kind of motor has a higher power density and better performance than induction machines. As I told you before, in permanent magnet synchronous motors, excitation is replaced by high energy permanent magnets. For instance, neodymium iron boron magnets. With those materials, volume is reduced and motor size can be about 30% smaller and about 10% more efficient. Next electromagnetic structure is a switch reluctance motor. In this motor, rotor manufacturing is very simple because it consists only on iron. No currents and no permanent magnets are needed. This is very important because the cost of permanent magnets increases in a very sharp way from time to time. The stator coils are concentrated and they are suitable for traction because of their high torque, robustness, simplicity of manufacture, and because the electronics and control required are simple. The next electromagnetic structure is a brassless DC machine. They come from DC commutator motors. In the past, DC machines were the traditional machines in electrical traction, but because the speed can be controlled quite easily. But DC commutator motors has some disadvantages, like their costly construction and maintenance of collector and brushes. DC brushless motor have permanent magnets instead of field winding. Computation is done electronically instead of mechanically. The permanent magnets are placed in the rotor instead of the stator, and the armature coil are housed in the stator, so no collector is needed to carry out the currents to the rotor like in the DC commutator machine. Its operation is based on sequential supply of each of the phases of the stator in synchronism with the rotor movement. And the last electromagnetic structure is axial flux motors. Previous motors were all of them radial flux motors, which are the most and of the commercially available ones. Typically, axial flux motors are synchronous motors with permanent magnets. They can easily be integrated directly into the vehicle wheel, optimizing the space and simplifying the mechanical couplings between the motor and the wheel. They have a stator and a rotor arranged aligned with the shaft, and the magnetic flux is parallel to the shaft. The only disadvantage is that radial stresses can appear, but they can overcome them, for instance, with double-sided stator. And let's have a look also to the first commercially available electric vehicle. We can find in this list the first electric vehicles that some vendors started to propose. Most of them are synchronous motors. For instance, the one for Mitsubishi, Peugeot, and Citroën with permanent magnet synchronous motor, 47 kilowatts at and 180 Newton measure. The Renault CE with a 70 kilowatts permanent magnet synchronous motors. But the main difference is between Tesla, which proposed an induction motor, a 185 kilowatts induction motor. In the next slide, we can see the characteristics of the Tesla Roadster motor, and the graphs show a comparison between this motor and an internal combustion motor for a high performance car. In black, we can see the graph for the petrol motor, and in red, we can see the torque characteristic for this motor, for the induction motor. We can see that at lower speed, the internal combustion motor has a very low torque, but the induction motor can provide the maximum torque, and also the speed range can be extended with an electric, in this case with an induction motor. So let's see a practical example about designing a permanent magnet synchronous motor for an electrical vehicle. The design process of an electrical motor is an iterative process. Losses depends on temperature, and temperature depends on losses. In the past, multiple packages were used. Today, I'm going to use itzer flux motor software, which is a software that can have into account the magnetic design, the thermal design, the drive for the motor, and also issues related to noise and vibration. So let's start with the specifications to design this motor. It is a small motor for an electric forklift. The maximum continuous torque we need is 55 newton meters at 300 RPM. That is a power of 17.3 kilowatts. The available voltage on the batteries is 300 volts, and we will consider an ambient temperature of 100 Celsius degrees because it is because of the enclosure of the motor. So we usually start with some previous computations in order to have some information. So assuming an efficiency of the motor of 94%, the input power of the motor should be 18.4 kilowatts. From the voltage on the battery, we can extract the voltage available to feed the motor. So considering a hexagon tracking control strategy for the inverter, that is 233 volts. And we can, from this voltage and the power, we can get estimating a power factor of 0.85. We can estimate the current to supply the motor, that is 53 amps. To start to design the motor, we start with this equation. This equation allows to get the dimension of the rotor from needed torque. So the torque is a function of the square of the rotor diameter and the stack length and the magnetic pressure. In the next table, we can see different magnetic pressure for several electromagnetic structures, depending also on the cooling conditions. In our motor, we have selected a magnetic pressure of 4 because it is a liquid-cooled machine, and we will get the highest value of this range. So, assuming a ratio of between the stack length and rotor diameter of 1.5, we get that the rotor diameter should be 95 millimeters and stack length 124 millimeters. So let's simulate the motor. For that, I propose to open the software and start defining the geometry of the motor. As I told you before, we are going to use an altered flux motor, and we will select to start a synchronous machine, permanent synchronous machine with inner rotor. So we will open the motor factory to start defining the geometry and all the input data. Okay. And here, this screen, we can see all the buttons to define all the input data. So we will start with the topology, and we have a general view of the initial geometry. We are going to modify this geometry in order to achieve the specifications we saw at the beginning. So I'm going to change the mode to define the motor. So the stator inner diameter is computed automatically, and we will start with the dimension, the rotor dimension, which are the one we have computed. So we have got a outer diameter of 95 millimeters. We have also a stack length of 124 millimeters. We will modify a shaft diameter to 32, for instance, and we will change the number of poles to 4. With those changes, we get this this machine. We still need to perform some changes. In this case, we will modify the number of slots, and we can see that the stator yoke is still too thick, so we will reduce it to 170. Okay, we have finished. We can start with the housing. Housing is important for thermal analysis. In this case, due to time restrictions, we will skip thermal analysis. So it's not necessary to define the housing for the magnetic analysis. We can design the shaft. So we will input some numbers. It is not also relevant for the electromagnetic analysis, but it helps you to see the process. So we will use for instance, a diameter of 28 and 25 at each side of the motor, and an extension of only 20 millimeters on one side and 40, that's 50 millimeters on the other side. So that's the resulting geometry for the shaft. Let's continue with the rotor. For that, we can see that proposed geometry has a surface magnet, and we want to use a synchronous machine that typically we use interior permanent magnets. So I'm going to change the shape of this magnet. I'm going to use V-block permanent magnets, and we will select according to the geometry I want to define this option. So now I need to modify some dimensions. We will modify the thickness of the magnet to 6 millimeters. We will modify also the magnet length to 24 millimeters. The angle we will leave as 150. Some dimensions like the distance with the rotor surface. Yeah, it is 1 millimeter, 2 millimeters for the web. This. Some of these changes are engineering changes that, according to the experience. So when applying these changes, we get that geometry. Next is we can set magnet direction. We leave as default, and with that we have completed the rotor definition. We can start with the stator definition, and we also will change the shape of this the stator slots. So I will use parallel tooth. I want to have parallel tooth, and this one is convenient for me for the data I need to define the slot. So I'm applying the changes, and I will modify the size of the slots. So I want a slot for 18. We have teeth width of 4 millimeters. We want some dimensions to be 1, the slot opening to be 2, and this angle to be 15 degrees. And with that, we got this that shape. And to finish the winding definition, we need to go to the tab winding. I want we have several ways to define the winding, from auto to expert. I will use advanced because it allows me to define with many options and in a very easy way the kind of winding I want to design. So in this case, we have a 36 slot. Of course, I performed some previous computation, so I have all those numbers on my head, but it takes sometimes it's not automatic to get those numbers. So we have for diametral winding coil pitch is 9, but in order to reduce harmonic, we will use a short pitch that is only 8 slots. The number of coils per pole and phase is okay. It is computed automatically for the software. We will modify also the pole distribution. We will use per pole. The number of parallel paths, we will use 4. We want to have 4 coils in parallel. The type of winding, we will use lap, and we will leave the phase sequence. So I'm applying all those changes. Let's define also the coil. Here we have a cross-section of the slot with some conductors placed on it. We have some options to modify the shape of the conductors. We will leave the ground conductor. We will also use a random orthocyclic position and the other options. Okay, group, for instance. We will define the number of turns. We previously compute that we need according to the voltage on the available to feed to supply the motor. We need 14 slots. The number of wires strands in hand should be 1, and the wire diameter will leave us 1.2. I will apply all the changes, and we get that conductors distribution in the slot. So you can have some physical feedback to check they match. They are able to be placed on the slot. And we have some useful information like the automotive forces, assume of the 3 phases, also the harmonics that we can get with this winding, and the winding factors. We can see that for the first harmonic, winding factor is high enough. So let's go to winding. Tap cooling is not available because we are not going to perform any thermal analysis, so we don't need to define the conditions, thermal conditions. And the last thing to define are materials. In this case, we will leave material for the shaft by default. We will replace material for the magnets. We will move to neodymium iron bottom, and we will leave also the materials for the magnetic circuit, both in the rotor and the stator. Coil conductor are copper, and insulator Nomex. So I'm applying all changes. With that, I have completed the definition of the motor, and then we can go to text menu where we have several predefined computation. So let me define the computation, and I will try to explain later what is during computation what is each option for. So we are going to guess get the performance of the machine, as it is we need a motor for a wider range of speed and torque, typically in e-mobility. So I want to get performance of the motor for a wide range of torque and speed. So I'm going to take this kind of analysis. So we are going to define some thermal. In this case, I have been limited to time, so I will input. I have estimated an initial temperature. I mean, a mean temperature of the motor of 140 Celsius degree. That is 40 degrees over the ambient temperature. We are going to define the electronics. We will define the inverter control strategy, and we will say that the available voltage from the DC bus is 300 volts. And from the mechanics, we will set up at 10, for instance, 10 watts for a reference speed of 1000 RPM. We compute that the current to feed the motor was 53 amps, and the way to command to control the motor is maximum torque per voltage. The maximum speed, we want to speed from the base speed to the maximum speed at 6,000 RPMs. So I apply all changes, and I let the software compute the performance of our motor. So we can see in the lower bar that the computation is running. So I can try to explain some of the features already embedded in the software. With open circuit, we can get the Cogging torque, which is the torque between the magnets and the electromagnetic structure of the stator, with no currents in the rotor. This is something you can note when you move the rotor in a machine, and you feel a drag torque and an accelerating torque. We can compute also in this with this option the back EMF induced in the windings, in the stator windings. With model, we can have some information about the fluxes, the inductances, and so on. In datasheet, we can get the performance of the motor, just general data like powers, efficiency, and so on. Thermal, you can assume we can get the temperature distribution in different parts of the machine. Working point, depending on the type of supply, with sine wave or square wave. This is typically a permanent magnet synchronous machine. This is typically a brushless DC motor, which we have seen in the previous presentation. And performance mapping, which is the computation we are carrying out. We have also the possibility to perform some noise and vibrations analysis, but this is not the goal of this webinar. And while software solves this example, we can also see the links to finite element tools, flux 2D, also to flux skew to consider the skew of the rotor or the stator, and also to optimization tool like HyperStudy, which allows to optimize automatically our motor, defining some objective functions and some restrictions. So competition has already finished, and we can see some results. So we have a base speed, which is 300 RPM, more or less. This time is 3,169 RPMs. We can see that mechanical torque is nearly 55 Newton meters. I think maybe I made a small mistake in when inputting some data. It should be a little bit higher, but we are very close, in fact, to the value of 55. So we can check also the machine efficiency, nearly 94%. We estimate 94%. We are a little bit below, but in the same range. Of course, the line current is the one we have input, the line voltage. We can check also. Okay, then something can be affected to the results is that we estimated a power factor of 0.85, and in fact the power factor is nearly 0.94. We have also a maximum speed. We have a torque instead of 55. We have 17 Newton meters. Mechanical power has decreased to 11 kilowatts. The efficiency has also decreased to 88, but the line current is the same. We can see that the speed is 6 now. In this case, is 6,000 RPMs. And we can have also a look into the losses. At base speed, the total losses were 1,200 watts, and now it has increased to 1,300, nearly 400 watts. Iron losses, of course, have doubled because of the increase of frequency. Joule losses are the same because the current has been kept to the same value of 53, and the mechanical losses which are speed dependent, then they have been also increased. In this plot, we can see, for instance, the torque speed envelope. So we can see that nearly the 55 Newton meter torque up to at least 3,000 RPMs, and then how it decreases. In order to decrease the torque, we need to supply with a different Q axis current and direct axis current. Okay, that is something we have not spoke about, but it is related to the model. Something interesting, of course, we have many information, many plots, but something that it's quite interesting for me is the efficiency map, because I told you in e-mobility applications, it is the range of speed where the motor can operate is very wide, also for the torque, and then we want to know the efficiency of the motor in those ranges. So that's a very useful information in order to achieve and to estimate battery duration and so on. We have many other interesting plots, but I want to show you just one. This is the losses according also to speed and the torque. So we can expect more losses when we are talking about higher torque and also at higher speed. Okay, and that's this is what I wanted to show you regarding simulation of an electrical motor for e-mobility. So the goal to design and simulate an electrical motor for the given specification has been more or less achieved, I have to say. And to going back to the presentation, just to some very brief conclusion. So we have reviewed the technology, the different electromagnetic structures for powering e-mobility applications. We have seen how flux motors can help us to design and to simulate electrical motors for e-mobility, because it is a complete solution for the design of electrical machines, considering not only the motor simulation, but also the power supply, thermal design, and NVH, and it can be also coupled with hyper study. So I think it's time for questions. So if you have any questions, I'd be pleased to answer them.
Thank you so much, Vicente. That was really very informative, and I'm sure all the attendees would have definitely enjoyed and got the queries clarified, or got more information about the electromagnetic simulation, about the motor used in the electric vehicle. Due to shortage of time, we have to request you, please send your questions or your feedbacks your suggestions to our email address, either to Vicente, VICENTE at apaengineering.com, or to my email address, Swami, SWAMI at apaengineering.com. We're sure that we will be replying all your questions, and we'll take your suggestions as well. And again, I take this opportunity to thank each one of you for your participation today. I'm sure you all had a very good session, as I did from Dr. Aucejo's presentation today. Thank you very much again joining, and thank you, Vicente, for the great work.
Thank you all of you for attending this webinar. We hope to see you next one. Have a nice day.
Yeah. Bye-bye.